Okay, hi everyone. My name is Guy Pimentel. I'm from the University of Leiden in Amsterdam, and I want to tell you today about the Cosmological Bootstrap. So the organizers asked me to give some updates on this new set of tools and developments in trying to understand the initial conditions of the universe better. Great. So I will start by acknowledging my wonderful collaborators who have really informed and shaped my understanding of this topic. So it's based on recent work the past couple years with Nima, Daniel, Wei Ming, Carlos, Austin, Hayden, and also based on some work from now a decade ago with Juan. And I must say also that there is also very interesting related work by various people. I listed a few of them here in this slide. I'm sure I'm forgetting someone. And as I'll try to convince you, this is a topic really on its infancy, and there is quite a lot to be done. So a lot of room for people to join and explore this exciting new field, trying to understand better the structure of primordial correlation functions. Okay, so the main question that drives this research program is the question of the origin of structure in the universe. So we want to understand. We see structure all around us. We see galaxies, we see stars, we see fluctuations in the cosmic microwave background radiation. So the question is, what seeded them, and what are those seeds made of? So the main tool to address this question is the study of cosmological correlators, study of the statistics of distributions of galaxies and of the photons of the CMB in the sky. In fact, I think that the cosmological correlators are really our only window to access the physics of the very early universe. So we correlate things at large scales, and it tells us about the extremely early universe. So being so important, understanding them not just observationally, it's an important goal of observational cosmology to constrain and detect primordial non-Gaussianity, cosmological correlators. But it's also important that the theory is well developed and that we know if and when we detect something, what kind of physics we are inferring from this detection. So this is the bird's eye view of what I will show you in the next 40-something minutes. I'll show you that there's a new perspective of how you should think of the very early universe. It can be thought of as a collider experiment run at extremely high energies. And cosmological correlators are really the scattering amplitudes of this experiment. Moreover, cosmological correlators, they contain scattering amplitudes. So it's not just an analogy to collider physics, but you should really think of these cosmological correlation functions as some mathematical objects, at least in their formal structure, that contain flat space dynamics and scattering amplitudes in a precise sense. And these new tools of the cosmological bootstrap are conceptually I think important, but also practically very useful to compute things that we weren't able to before and give us new handles on the statistics of the primordial fluctuations. So this is the big picture. So let me just set the stage by reviewing what we know about primordial fluctuations. So for this audience, I can be brief here, right? So primordial fluctuations are responsible for forming structure in the whole universe, and we infer their statistics from the distribution of galaxies and the temperature fluctuations in the CMB. And then from these plots of the galaxy and the CMB distribution, we can infer the ingredients of the universe. We can infer the amount of dark matter, we can infer the amount of dark energy, and so on. And moreover, if we run the clock backwards to the hot Big Bang, then we know that we needed almost Gaussian initial conditions, or to very good approximation Gaussian initial conditions They're almost scale invariant with a slight tilt and an amplitude that's being detected with high significance, both the amplitude and the tilt. So these are two numbers that characterize primordial fluctuations, and we want to understand what goes beyond these two numbers. And so my focus during the talk will be about the initial conditions. So of course, it's a famous puzzle that these correlations are imprinted at long distances right at the hot Big Bang, so they look acausal. And we have a paradigm, a solution to this puzzle. The idea that actually before the hot Big Bang era, there was an earlier period of cosmic inflation, which was really designed to solve other problems, to explain why the universe is so big and homogeneous and so on. Moreover, it gives us a mechanism to source the initial conditions. The initial conditions are really quantum mechanical fluctuations that get stretched to very long distances. So the initial conditions are set at the end of inflation. So the real Big Bang happened even earlier. Great. So this is 40-year-old story. But an important theme of the talk will be the emergence of time from spatial correlations. So if you look here in the plot, you will see that if I look in the sky into things that were correlated at shorter distance scales, they were sourced later during inflation. While if I look at longer distance scales in the sky, they have to do with fluctuations that were sourced earlier during inflation. So even though I don't have access to the chronology of what happened during inflation, I can infer by looking at correlation functions over different baselines in the sky. So this is an important theme that we'll use heavily in exploring the structure of higher point correlation functions. So, an important question is to figure out what is this inflaton particle? What's really sourcing the quantum fluctuations? Okay. So the precise mechanism of inflation is still a big mystery, and all we really know is that there is this scalar field that sources the fluctuation, but we don't really know what it is. We would like to have a magnifying glass and figure out what it's made of. If it's really an elementary particle, or if it's really something composite made of other things, if it's a excitation of some extended objects. So there are various scenarios. For example, I list a few of them in this slide. It could be some string excitation. It could be some particle in a supersymmetric multiplet. It could even be the Higgs particle in some scenarios. It could be the axion that solves the strong CP problem, or an axion-like particle from string compactification. It could be a collective mode of some extended object like a brane. So there are various scenarios, and we don't really know which one is responsible for inflation. So to uncover that, to really learn about the microphysics of inflation, we need more information. So in the past few years, especially the past 6 years or so, we have a new picture of what inflation is, or some qualitative new way of thinking about inflation. So you can think of inflation really as a collider experiment run at extremely high energy. So inflation happens at a certain energy scale. We have the Hubble scale during inflation, and that hasn't been measured because we haven't detected the primordial gravitational waves yet. But from a model builder perspective, it's typical that the energy scale of inflation is huge, perhaps billions of times higher than the TeV scale of the LHC. So this is an amazing opportunity to do particle physics at energy scales way beyond the reach of terrestrial colliders. So can we leverage this picture of the early universe as a collider experiment? So we have measured here the 2-point function of density fluctuations, and we want to measure the 2-point function of primordial gravitational waves. And the focus of my talk will be in higher point correlation functions of the scalar fluctuations. Okay, so I'm depicting them here. And to contrast the story with what happens in a collider, here's a collider experiment, some snapshot of collision atlas at the LHC. So there's some interesting microphysics that happens at the center of the collision. And then there's all of these detectors that collect debris and stuff that leaves the collider. And we need to infer what's the microphysics responsible for this pattern that we see in the detectors. And in the case of cosmology and figuring out what happened during inflation, it's the inside out version of this picture. We sit here on Earth, we think of it as a center of our universe, and then we see, or perhaps take into account that we are being, there's some center of mass frame, which we see the CMB homogeneously, and then we collect all of these photons from the CMB and from galaxies, and we need to infer, run the clock backwards and infer what sets up the initial conditions, and even earlier to see what gives rise to the specific patterns of the correlations that we see in the sky. So if we're going to go with this collider analogy, let me just explain a couple more things about it. So for a clear question is, what is it that's colliding if we're talking about collider experiments? And another question is how they collide. So in colliders, things that we can collide, we can use for probing microphysics, are objects with large two-point functions, because then we can move them around. We can prepare a beam of particles here, move them there, they don't decay. So objects with large two-point functions will be the ones that are responsible for collisions. And in the case of inflation, what collides are particles with large two-point functions. So in our case, we'll mostly be working with the Inflaton, but perhaps also primordial gravitational waves, because they are light, massless, so we do expect them to be stable, if even though they might have a weak overall strength of the two-point function. So now, how do they collide? So to infer microphysics, in collider experiments, we just mash these external probe particles, and then here you see that they're being smashed. So they're colliding, and depending on the pattern of the collision, I can infer some new states that were responsible for the pattern that I see. So that's how I learned about microphysics, right? You see, if I scatter fermions in the standard model, I can infer the existence of W bosons, or I can infer, if I scatter W bosons, I can infer the existence of the Higgs, and so on. Great. So in the case of inflation, so we know that the inflaton and the graviton have large two-point functions, but then to infer microphysics of maybe new states that we don't have direct access to, that might be heavier, their power is redshifted away, we don't see them directly, but maybe they leave interesting imprints when they decay into the more stable inflaton particles. So that's why primordial non-Gaussianity is so rich, because it encodes the specific microphysics, the dynamics of inflation. So another interesting thing now is going back to this point of the analogy between cosmology and scattering amplitudes, is there is a very precise, I'll get back to it during the talk later, there's a very precise sense in which cosmological correlators contain flat space scattering amplitude. So there is a mathematical limit, I'll describe this limit in a few minutes, in which if I take the formula, the analytical formula of the cosmological correlator, and I probe this limit, it's not physical in the sense, I can't probe this limit in the sky, but I can take the formula and go to these limits of unphysical momenta, and then I'll see the cosmological correlator diverges. But the exciting thing is that the coefficient, the residue in front of the divergence, has a nice physical interpretation. It's a flat space scattering amplitude. So when I probe this limit, what I'm really doing is I'm zooming in, I'm boxing in all the interesting dynamics that gives rise to the correlation function, and I'm boxing it in so much that the fluctuations don't know they're in curved space yet. So the residue is a flat space scattering amplitude. So the lesson from here is that the richness and beauty of the S matrix program, of all the structure, the deep mathematical structure of flat space scattering amplitudes, is contained in cosmological correlation functions. And cosmological correlators encode this S matrix in a rich, very precise way. So this is important to keep in the back of your head, because if you ask, well, how are we able to know that we'll be able to go so much farther than we have been so far in the study of cosmological correlators? It's because of this connection, this deep connection to flat space scattering amplitudes. So a question that permeates this whole program is to map the space of consistent cosmological correlators. I want to understand, can we classify all possible correlators? I could pick a model and calculate its consequences observationally, but what can we say about more generally about the menu of possibilities? Does anything go, or is there some rigidity that allows me to classify possible cosmological correlation functions? So it turns out that under a set of assumptions that I will describe in a few minutes, that 3 and 4 point functions can be classified on fairly general grounds. And 3 point functions are, in fact, consistent, more or less unique. The richness, the menu of possibilities becomes wider when I go to the 4 point function. And so I'll describe the 4 point function now for you, the one that will be attacking the next part of the talk. And these 3 point functions that you see in my background, the ones that come from more realistic models of inflation, they can really be thought of as coming from this building block. I'll describe that to you briefly later in the talk. So this is my main subject for the next few minutes. So this, I have some particle that I can't observe directly, maybe ultra heavy for collider standards, but light during inflation because of the Hubble scale during inflation. It gets pair produced, then it decays into the inflatons, and then the inflatons at the hot Big Bang source a very specific pattern of density fluctuations. And this pattern will tell me about the details of this new particle. That's how I infer the details about this new particle. Moreover, this particle, now I have various handles because I have a 4 point function. So I can change the various handles. And then what I'm doing is I'm creating hierarchies of the times at which the various fluctuations are being sourced. Remember that larger scales are earlier times. So then as I change the shape of the correlator, I'm probing different times during inflation. And then this blue particle needs to propagate consistently in the background geometry. So it can't be that anything goes for the shape of this cosmological correlator. It needs to be consistent with this blue particle flying through the expanding cosmology and really tracing the background cosmology. So that's another reason why these heavier particles are interesting. They really confirm the paradigm that the background geometry was given by de Sitter space, for example, or quasi-de Sitter space. So how do we compute this? Is it easy to calculate? In fact, it's not easy to calculate if you try to follow standard time evolution tools of perturbation theory, because these mode functions in de Sitter are complicated. You need to do some nested time integrals depending on if the times in which the two decays happen are nearby or there's a large hierarchy. It's a fairly complicated process, and until a few years ago we could only plot the results numerically, but we had no analytic understanding. And even if someone handed you the formula, we didn't know how to decode the formula and tell you, oh, this formula is telling me about this particular process at which at this time this decay happens, and at that time that decay happens, and so on. So that's what this program is trying to achieve. Not just compute the analytic templates, but to distill the physics out of the templates, out of the various parts of the template, be able to tell you this is what happened here, this is what happened there, and this is what happens at short distances, and so on. So this is where the bootstrap philosophy comes in and becomes very powerful. So the bootstrap is something that was proposed in the 60s and had success stories in the 80s and a whole revival in the early to mid 2000s, early 2010s. So the idea is that we focus on simple enough observables, okay, some very simple observables, and what we can hope to measure in the sky, or maybe 3, 4, who knows, maybe 5-point functions, but not like 20-point functions, which in principle, if I write a specific model, I have the machinery to go to very complicated correlators. But we are interested in simple correlators, 3, 4-point functions. And then the structure is so tight, the requirements that these correlators need to satisfy, consistent with symmetry, consistent with local physics happening during inflation, and the physics needs to be unitary, probabilities need to add up to 1. This is so constraining that in fact you can make fairly general statements without talking about specific models. You can just ask for the answer to be consistent with all of these requirements, and you will pin down the answer completely. So this is the bootstrap philosophy. And here's just a very simple example of how this bootstrap philosophy is powerful. So if I just study 2-to-2 scattering of scalar particles in flat space, the S matrix that you could measure, I don't know, for example, pions in a collider experiment, you could say, well, what if there are all sorts of extra states showing up? And I could write all sorts of Lagrangians and models for the microphysics of these external probes. So now if I work on weak coupling, the 3-level approximation, in fact, if I use symmetry, locality, and unitarity, I can write down a formula that gives me everything. This is the formula. As a model builder, your only freedom will be in writing the spectrum of these particles, the masses and the spins, and the coupling strengths. But not just that, and maybe if you have a finite energy range, maybe there's some contact interactions that you don't know where they come from. Even the contact interactions, they have a rigid structure. So you can just write down, not just say that these are the possibilities, this is easy to argue for, but based on consistency, you can write down the answer. You don't need to go to the machinery of field theory and Feynman diagrams. You can just write down the full answer, just from trying to bootstrap yourself to the answer. So we want to run a similar program in cosmology. That's what the Cosmological Bootstrap is trying to do. And I'll show you the successes we've had so far. So in particular, this example that I just gave you, this case study of the flat space S matrix for 2-to-2 scattering, is very much analogous to the 4-point diagram that I just showed you. And I will prove that in inflation we can do the exact same thing. It's the first success story that we've had in this bootstrap program. So first of all, in inflation, we're going to assume maximal symmetry, at least for this first part. In particular, I will assume that inflation is very well described by de Sitter space, at least for the scales that we probe in the sky. And that gives me a lot of symmetry, perhaps more than what we can really infer from the data so far. In particular, there are de Sitter boosts, analogous symmetries to boost symmetries. And they are very powerful, as I'll show you. So not just translation, rotation symmetry, and scaling symmetry that we can infer from measurements of the 2-point function. I'm going to add 3 extra symmetries, which is really the maximum that I can impose on the cosmological correlators. And now for the singularity structure. What are the interesting singularities that this cosmological correlator can have? So here I am going to stop sharing for a second, and I'm going to go to the blackboard. So this is a sketch of the 4-point function that I'm trying to bootstrap. I'm trying to not do time evolution, just ask that some objects here is a function of the wavelengths of the various states, has the right singularity structure, has the right mathematical structure to encode the dynamics of this process here. So if I take the momenta of the particles, so the particles, it's a 3D pattern, they have wavelengths and wave numbers, Ki. So just some jargon, it makes sense to talk about their absolute values, and I'm just going to remove the arrow and call these energies. So if you think about it for a second, to compute this absolute value, I need to take a square root of k dot k, right? So in particular, it has a branch cut, the square root. So it makes sense to talk about negative energies, even though these are not, if I have just wave numbers in the sky, these absolute values are always positive, okay? But if I dare to go into negative energies, then these are the singularities of this particular cosmological correlator. First of all, in the physical region, as I said, there should be no singularities. In fact, and this is a requirement. If you try to bootstrap the 4-point function, you will see that typically it's possible to have singularities in the physical region, and we're gonna forbid those from appearing in the answer. So this is one requirement. Second requirement is that if I take the sum of the total energies of the 4 legs and I send them to 0, as I alluded to earlier in the talk, what I'm really doing is I'm really squashing, I'm sending all the fluctuations to very short distances, very early times. So I should really see that the correlator diverges, but the residue up front is the flat space scattering amplitude, which for this process is very simple to write down. It's related to the formula I showed you a few slides ago. So this is one requirement. It should go like 1 over E total to a certain power times the formula that I showed to you a few slides ago for the S-matrix bootstrap. But there are other requirements. For this diagram, there are 2 other singularities. So there's one singularity in which the energy is just flowing into the left vertex, but not touching the right vertex, go to 0. Okay? So if I send K1 plus K2 plus the exchange momentum, that we call it S, in analogy with the Mandel-Stan variable S for 1 to 2 going to 3 to 4. Okay? If I take this variable here and take its energy, call it S without an arrow, and I send this sum of energies to 0, then what happens is that now I'm zooming into this process. So this part of the whole process should happen in flat space, while this part of the process can continue happening in cosmology. But now you have 3-point function on the right, 3-point function on the left. And the symmetries are so powerful that 3-point functions are completely pinned by kinematics. So that gives another handle to the dynamics. Likewise, there will be a limit in which I send the energies on the right to 0, while keeping the stuff on the left untouched. So an object consistent with symmetries and only these 4 singularities, I claim is unique. And that's the answer to the cosmological correlator. And notice that there is no time being mentioned anywhere here. So this is what we're going to achieve the next couple of minutes. So now let me go back to the slides. So this is just a little appetizer of how we leverage those singularities to get a really concrete equation that we can solve without talking about time evolution. So the idea is that I'll have some stuff happening on the left that's related to moving this left vertex around up and down in time. And likewise, there will be another equation related to moving the right vertex up and down in time. And there are 2 physically interesting limits in the physical region. If I make the wave numbers on the left comparable to the wave numbers on the right, then all the physics is really happening at the same time. And it should be dominated by something that looks like contact interactions, that looks like your typical equilateral-like non-Gaussianity. While now if I create a hierarchy, on the other hand, and I make the modes on the left have much longer wavelength than the modes on the right, then I create a big hierarchy in the times, and the imprint of the particle tracing the background geometry should become extremely clear. So this is where the motivation for the equation comes from. And this is the concrete equation that you get. So this delta U operator is some hypergeometric operator. In the discussion session, I can spell it out more if you're interested. So there's some specific second order, I should mention differential operator, that if you act on it if you wish, you're acting on the 4-point function from the left and collapsing this internal propagator. That's how the mass of the particle, the information about the mass of the particle comes in. I'm working with scalars for now. Then I collapse this internal propagator and I get a contact interaction, in which only one time is interesting. So you only have this total energy singularity. So this is much easier to classify. Okay, this delta U knows about this left singularity, and the contact interaction knows about the total energy singularity. And there will be likewise an equation acts on the right and collapses the propagator moving to the left. Okay, so that's how all the singularities, the left, E left, the E right, and the E total singularities will play a role in bootstrapping the correlator. And notice that there's no time evolution anywhere here. Everything is spatial patterns. Just an analogy as to how you should think of it. In flat space, there is some propagator that you hit the exchange scattering amplitude with, and you get some contact scattering amplitude. So just boundary conditions, because it's a second order differential equation. One is related to sending this left energy to zero that I showed you in the blackboard. And then the 4-point function should factorize into a product of 3-point functions. Should really pull the correlator apart. And 3-point functions are fully fixed by kinematics. So that's why this limit is very simple. And moreover, there should be no singularity when momenta are collinear. And this folded type of singularity is phenomenologically interesting. And if you, for example, relax the assumption that the fluctuations start their life in the vacuum state, it's possible to induce singularities here, but we're not going to allow for that. It's interesting to investigate, but we don't do that here. And that's it. So now you have a differential equation with boundary conditions, ordinary differential equation you can solve. You can use the whole machinery of ordinary differential equations to solve it, and we have a very explicit solution. We know where all the singularities are. We understand the physics of every singular point. And I'm just going to describe to you the solution. So in the limit in which all momenta are comparable, I get some 4-point function that doesn't really have features. It's decaying as I'm creating some hierarchy, just because this particle needs to start traveling, gets redshifted away. But then for a long time, for a long range of scales, this is well fit by effective field theory operators, just hard contact interactions. As I dial the hierarchy, then this particle needs to travel more than 1 Hubble volume during inflation, picks up a phase. And if I really blow up the feature, you can see clearly this is amazing, right? In the spatial pattern in the sky, you're seeing time evolution of this particle tracing the inflationary background. So this is how you will see in the inflationary non-Gaussianity, you will infer the mass of the particle. You'll be able to check that the particle was traveling through the de Sitter geometry during inflation. So this is an extremely general result, okay? And I described to you how it works for scalar particles. You could ask, well, what about spin? Do we need to go back to the drawing board and start again? And this is where symmetry becomes very, very useful. It turns out that there are certain operations that I'll be happy to discuss live. We call weight shifting operators that simply allow you to take this building block that we were going through in quite a bit of detail and apply some derivatives to this, just some very simple operations, very systematic operations You don't need to solve any new differential equation, and you get the solutions for new diagrams for exchange of spin. Well, from the Lagrangian perspective, spinning particles become intractable very quickly. Not just that, you can do another limit. You can take a limit, for example, of one of the legs being very soft. You can treat it in the bootstrap also. And look, the resulting objects is interesting. You get a 3-point function of 3 momenta here on a soft background of one very long mode of the inflaton plus the de Sitter background geometry. So these 3 other modes really think that they are on something that is not quite the Sitter space, because there is this very long wavelength mode redshifting way slowly. So this explains the richness of slow-roll inflation bispectra, the ones that are shown in my virtual background. They're really coming from the Sitter 4-point functions in the soft limit. And we can reproduce many of the famous results in the literature by following this procedure, but now we know the answer for any mass and any spin. We can just classify all possible slow roll bispectra. We can repeat this bootstrap philosophy and ask about gravitons. Of course, we haven't measured the 2-point function of gravitons, but non-Gaussianity in the gravitational sector is very interesting because it's not constrained. It could very well be highly non-Gaussian in the gravitational sector. So can we produce a similar menu of shapes of non-Gaussianity involving gravitons? And gravitons are more constraining and very interesting because they're spinning particles and massless. So they have very tight requirements of consistency if they are to propagate in a way that is unitary, local, and causal. So famously, Weinberg showed in the 60s that in flat space, if you couple a field theory to gravitons, the graviton wants to couple, requires you to couple to every particle species in the theory with the same strength, which is what we know and love, the equivalence principle. So can we bootstrap the equivalence principle in cosmology without writing a Lagrangian? And the answer is yes, we can. You could imagine taking the 4-point function that I was describing to you just a couple minutes ago and apply this weight shifting technology to spin up one of the legs and get a graviton leg, massless spin 2. And you will find that it's inconsistent. There's actually a very subtle breaking of boost symmetry that I'll be happy to discuss with you live. And the only way to cure this problem is to force the graviton to couple to all the other particles, has to couple to all the other particles. So this is what these 2 other diagrams are doing. But not just that, it has to couple to the other particles with the right strength, in the same strength. So that's how you discover the equivalence principle. And not just that, you actually compute the non-Gaussianity. So this is what we did last year. Okay, I have just a few minutes left. I'm going to flash this very quickly. So certain correlators are, in fact, much simpler. When you solve the differential equation, instead of getting some generalized Bessel function or some very complicated objects, some correlators are simple rational functions. So it asks the question, can we find a different strategy that allows us to compute these rational correlators faster than through this differential equation technology? And this is something we proposed in a paper from around a month ago that involves a few steps, cutting, gluing, lifting. And it's really using a lot of technology developed in particular by the Cambridge group over the last year or so. So now we understand much better the consequences of locality and unitarity, for example. I should also mention Paulo Benincasa, who's now at the Max Planck Institute, did a lot of important work in this area. So, for example, there are nice cutting rules of cosmological correlators. So they follow really from locality, the structure of the propagator, and unitarity. So they allow you to take this 4-point function, take a particular operation, sometimes I call it star, doesn't matter what it is. Because of locality and unitarity, there's a certain combination of the 4-point function that allows you to cut the propagator and gives you something that is really the 3-point function. not in the limits for any values of the momenta, unlike the boundary condition that I explained earlier in the talk. Not just that, if now we know how to deform the correlator into complex values of momenta or complex values of energy and use some dispersion relation type of argument and use the scattering amplitudes in the singular limits and try to reconstruct. So you see when z equals 0, I'm back to the original correlator. And I can use some nice complex analysis to go to these limits, take these limits here, the scattering amplitude, and glue them in a consistent way and get back the original cosmological correlator. Great. And finally, it turns out to be much simpler to work in the fake cosmology in which there is no space-time expansion. You do everything in flat space. You compute some analog of primordial non-Gaussianity in flat space in which you abruptly stop time evolution. So this object is unphysical, but it has a very simple, it has the same singularities as the real cosmological correlator, but structurally it's much easier to work with. And then there's some lifting that you can do. Again, very similar to these weight shifting operators, some sort of derivatives and blah, 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 that you can act on the flat space correlator and get the real de Sitter answer. Just to give you like a little flavor of it, if you take a mode function of a free scalar field in de Sitter, you can get it just from applying a simple differential operator into a standard plane wave in flat space. So this is some more complicated version of this simple observation. Okay, so I'm really running thin on time, but I'll just quickly flash what's in the future. I just gave you a 45-minute presentation about simplest tree-level processes and just about the shapes. Can we say something about the sizes? Can we say something about detectability? And I highly recommend you to check the talk by Alba Kalaja. She contributed a talk about how we, what are the roadblocks and how which shapes of non-Gaussianity have better prospects from, for example, from the CMB. It's a very interesting topic of research to figure out what happens at large-scale structure or even more futuristic probes like 21 centimeter or gravitational waves. Can we go beyond the symmetry paradigm, talk about slightly broken symmetries, or maybe other singularity structures like other mechanisms that source the primordial initial conditions? We can run the bootstrap in those. That would be extremely interesting. We would have really another menu of possibilities that would tell us just broad paradigms would produce different templates of non-Gaussianity. In particular, broken symmetries, relaxing this boost symmetry in this cutting, gluing, lifting procedure, and also the Cambridge group has been pushing towards relaxing this strong requirement of boost symmetry, and with remarkable successes. And these are two, I'll end with two more grand goals of this program. If we understand the structure of cosmological correlators, we really might be able to make general statements and carve the space of possibilities, not just the shapes of primordial correlation functions, but really, hopefully, be able to say something about the sizes or perhaps even the structure of the spectrum of consistent theories of inflation. Maybe we'll be able to infer, for example, if it's really some stringy UV completion, what kind of cosmological correlator should we have? Or is equilateral non-Gaussianity, can it be arbitrarily small, or it must have at least a certain size? So these are questions that have analogs in flat space and in which people have been making tremendous progress. Like even now, a few months ago, there's a lot of exciting new work in that direction. So we can hope to import some of that technology to cosmology. Maybe ultimately, more ambitiously, if we really want to push our understanding of the primordial universe to the Big Bang singularity, we might try to import some of the lessons of holography in string theory, where we learn that It's very useful to anchor yourself at some boundary of space-time and ask questions there. So it's very well understood in the case of negative cosmological constants and zero cosmological constant, the whole S matrix program. Here we're just in the first baby steps of learning how to ask questions of self-consistency at this hot Big Bang surface and inferring consistent time evolution, seeing the emergence of time from these very simple patterns. And ultimately, if we learn all the rules, we might be able to really push our boundaries of understanding all the way to the beginning of the universe. So I'll stop here. The early universe, the primordial fluctuations are really our rich source of information about, perhaps our only source of information about what happened at the beginning of the universe. They probe particle collisions at ultra high energies. And this bootstrap is conceptually, I think, a new perspective and also practically extremely useful. It's a new toolbox that allows us to decode primordial non-Gaussian in a way that we couldn't until a few years ago. Very excitingly, you see in these static patterns, you can really infer consistent time evolution. So we might be able to learn ultimately how to decode the hologram of the distribution of patterns in the hot Big Bang and infer what happened in the beginning of the universe. So I will stop here. I'm really looking forward to meeting you all in person and have a live discussion very soon. So thanks for watching.